one, we can go ahead and tackle that by just solving it out. And then two, we can also kind of buddy that up with using our graphing skills, graphing calculator. All right. So reminders on the SAT day, you got your 84s you can use, and also on that day, it is online, and you will have access to Desmos. Desmos, for those of you that have been using Desmos for graphing, you also have access to that. So there you go. Now with that, find the solutions. Those are the x-intercepts. Right there, we know how to solve that out. Okay, we can go old school. I think I'd have that right. So we can go old school with solving that, setting that thing to 0. And this is just part of what we've been talking about. That's a 2x. Okay, setting that to 0 using our skills of factoring. That's a quick factor. C is 0. That's a good old GCF. Okay, that's what we've been working on. What's the GCF here? Bring in the GCF. GCF is, 1x. Now, it's got a negative, so I would probably bring out a negative 1x. And then from there, what do we have left over? X and a negative 2. Okay? Nice. Okay. What's our solutions? Okay? One solution will always be 0. From right there. From that GCF that you brought out, that solution's going to be 0. No matter what you bring out for that GCF. If it's a negative x, if it's a 2x, if it's a 5,000x, it's going to turn out to be 0. The other one just depends on the problem. What's that going to be? It's going to be what? It's going to be 2. Okay? Now, from this point on, I got my x-intercepts, and then I can confirm that also with my graphing calculator. Okay? Now, the thing about this is that negative lead coefficient, when I go ready to calculate, when I go to graph this, I'm expecting this parabola to be opening what? Down. The lead coefficient, as we said, does a lot for us. So when I go to graph this thing to kind of confirm things are happening, or I didn't even have to do this by hand. Time is time on the SAT. So one thing I would probably just go ahead and do then is say, hey, negative x squared, what is it, plus 2x? Go graph that thing. I can just quickly look at that and say, boom, boom. My solutions were what? 0 and 2. I didn't have to even solve that out. Okay? Okay, 0 and 2. Yep, go ahead. 0 and 2, which confirms that what we got. It's opening down. So there are my, what did we just say? 0, 0, and what? 2, 0. Okay? Axis symmetry. Axis symmetry is, boom, right there in the middle between 0 and 2, which is our midpoint, reinforcing that midpoint of ours. Don't forget, x equals 1. Vertex, we can see clearly right there at what? 1, 1. And then we should know that that vertex is going to be a maximum from the get-go, all because of that negative. What did we just say? Maximum. And that value of that vertex, that's getting into that range that we have been working on second semester. That range, negative infinity, up, we hit a ceiling. That ceiling is that maximum. The value of, in this case, 1. It's coming right there at 1. The y-intercept, where's it crossing the y-axis at? Happens to be the one time where the x-intercept and y-intercept are one and the same. 0, 0. All that pieces together, we can look at our graph and say, boom, there it is. The x-intercepts do it. The vertex does it. That's going to be fine enough for a sketch of a graph. Okay? Doesn't need to be fancy. Okay, there we go. The graphing calculators are a powerful tool for that. Okay, you can solve it by hand. We definitely can do that as well. Okay, those two things together are helpful for you. Okay, All right, good question on that one, Kate. I guarantee you there'll be something graphing related with the quadratic on the SAT, so it's a good question there. Brianna? 10? Previous side, right? 10, 10, 10. 10, that's a good one to talk about. First thing is, we talked about this one yesterday. What does it equal? It equals 0. And when it equals 0, and when we look at the structure of that problem, it's in factor form. It's good to go. It's ready to go. Use that zero product property to bars. So when I look at that one, the solutions are already there for us. You're using that zero product property. Negative 5/7. Negative 2. Now this one though, I get a third solution. This is not a quadratic. Why is this one not a quadratic? I've got 1, 2, and 3. This one here, I had a GCF that I do care about. This GCF I brought out, it has a variable with it. So what's after a quadratic? Third degree, which we call a cubic. This is a cubic equation. And with a cubic equation, I can get not just 2 solutions, but I could get 3 solutions. Correct. It's just one small step. Okay? It's one small step. And next year in Algebra 2, that's where you're going to go. Algebra 1, focus usually up to 2 solutions. Who cares? It's one small step. We can get 3 solutions there. You're going to see 4 solutions, 5 solutions next year, whatevs. Okay? Now I care about that one because there is a variable there, and just like we did on that previous one Kate talked about, all right, hey, it's n equals 0, n equals -2, n equals -5/7. It's actually a cubic equation, not a quadratic. All right, we talked about it, no big deal. Okay, it's a good one to ask though. All right, so we're gonna keep throwing those small steps out there, looking at Algebra 2. All right, keep going. Yeah, Eva. 6. All right, 6. First thing is definitely not in standard. Let's play the rearrangement game. Add that 4 over, right? 4v squared gives me what? 1v squared plus 4v and then minus 32. As we did yesterday, okay? It just says choose the method of your own, okay? Choose your own adventure. I can't do square roots. Here, for myself, it's worthwhile to see if it can factor. Okay? Now, obviously we know the answers, but the reason why I would say it's worthwhile to see if this one can factor is because what is the A value? A is 1. That should be a quick determination if you can factor this. If I can't factor that, I'm going to use complete the square or quadratic formula. I can quickly look at factors of 32 and see if anything's going to give me a 4 out of that. What's factors of 32? 1 and 32, 2 and 16, 4 and 8, 6 no, 7 no, 8 no, and we're done. But as soon as you list off 4 and 8, we've done a ton of these things where you should realize a 4 and an 8, yeah, that's a way I could get a 4 out of that, right? So that 2 seconds that it takes us to list those out, this is factorable. I'm not going to worry about complete the square. I'm not going to worry about a quadratic formula. So I'm going to go straight to this right here. V what? I need a positive 4. I need a plus 8 and a minus 4 right there. Okay? And there's my 2 solutions. Negative what? 8 and what? 4. Which leads me down to, I believe, question 11. Question 11 is my SAT question with you. Okay. On question 11, if V is greater than 0, which of those is the value then you're going to select? Positive 4. Right. That's my SAT part with you. Okay. So you're not going to choose both of them. You're only going to choose the one that's greater than 0, which is code for positive solution. Okay. Good question off there. Okay. Anything else? Go once, go twice. We're sold. Make sure your name is on it. Throw it in the basket. Some circle work. Okay. Boom, that is the definition of a circle. We talked about that before, and I'm sure we definitely remember the definition of a circle, right? Nope, fair enough, I know. But that is the definition of a circle, okay? So a circle, you gotta have a center. And then you gotta tell yourself how big to open up that radius. You then spin it around and make that circle. That's what we have right there, okay? So it's a set of equidistant points from a given point called the center, okay? Now, just going back to your vocabulary, because as we worked through that circle stuff sometime in first semester, I don't remember when that was, but a segment that has one endpoint at the center and one point on the circle, one more time, is called my what? That is called my radius. Yep, radius. Now, something that have what we call congruent radii. So if we make one circle here, center with this 5-foot radius, spin it around, here's one circle. If I keep that locked and I come over here, I make another one with another 5-foot radius, what have I just created? What's that? I did another same one with a 5-foot. I made two circles that are congruent. Right, we call those just congruent circles. So to be congruent in terms of circles, you just got to have the same length of a radius or the same length of a diameter. Yeah, that's about it for what you call it. It's a little bit simpler than say looking at triangles and quadrilaterals and all that. Okay. All right. How about the next one, real quick? Segment that contains the center of a circle and both endpoints of that circle. That is our good old diameter. Goes through the center and has both endpoints on there. That is our good old diameter. Now, we know there's a few other pieces out of there. We talked about a couple other things. One more time, if that diameter gets shifted off of the center, okay, what do we call that segment? That's a chord. So let's reference that guy. That's a chord, okay? So if we get a segment that's shifted off of that center, endpoint to endpoint still in the circle, but not going through the center, that's a chord. And then if I get myself another a line that is coming through the circle, all right, coming through the circle, what do we call that one? Anybody remember? That's a secant. Okay, a secant that is a line that comes through the circle, intersects at two places like that. That is what we call our secant. Those are the chord may have been not a new one. Might have heard that before. Secant was probably a brand new one. And then we have one last other one. What was our other one? Anybody remember? It's the tangent. Anybody remember what the tangent did? Right. So a tangent just comes in. It could be a line, a segment, a ray, whatever. But as you just said, it comes in, just kind of kisses it, and moves on. It intersects it at just one specific point. We call that the point of tangency. And those are your major players for different bits and pieces of a circle. And we talked about some angles. Okay. What do we call that one there? An angle whose vertex is centered on the circle. That is our central angle. Pretty obvious because, well, vertex is where? On the center. And then we had something that's just part of a circle. So we call it an arc. Okay? That's where we get ourselves in arcs. Okay? Okay, we have we have 3 different types of arcs. Which, let's walk down memory lane because we're going to talk a lot about arcs now. Okay, we're going to use these arcs today in conjunction with perimeters and areas. So, reminder about an arc. They're all built around, first off, a semicircle. What do we remember about a semicircle? Semicircle is what? Right. Semicircle is exactly half a circle, which is what? Half a circle is how many degrees? Right, 180 degrees, right? So it's all built off of that. Looking at that circle again, let's remind ourselves how to name a semicircle. Can somebody point out an example of an arc that is considered to be a semicircle? Carter? ABC. Thank you for using those 3 points, because remember, it does need to be named as 3 points. That is an example of a semicircle. ABC definitely works. You got to tell me a starting point and an ending point. So you got to then tell me a middle one to tell me which direction you're looking at. Okay. All right. Now from there, we have the other two: a minor or a major. Less than 180 is a minor, right? So naming that minor, as you reminded us. Somebody give me an example of a minor. CB, CE, AB, DB. Those are all minors. How many points are we using? Just 2. Correct. Those are all examples of minor arcs. And you always will take the shortest route for that. Okay, when you say those 3 points, you're following that direction. There's a whole bunch of minor arcs up there. And then lastly, we have ourselves the major arc, right? Major arc is what? More than 180. Somebody want to give me a name of a major arc up there? A, C, D. So as you trace that out, it definitely appears to be more than 180 degrees, right? So as Carter said, ACD. Again, trace it out, make sure it does go more than 180 degrees, more than a semicircle. That appears to do so, okay? So just a little trip down memory lane in conjunction with these right here, okay? Reminding ourselves about some area here. So I was working through this morning, getting ourselves prepared for the next month of April. All right, we're gonna bring this all in, all right? Remind ourselves one more time, all of our area formulas. Area of a rectangle, I know we beat you in the head about it, but one more time, area of a rectangle is base times height, length times width, either one's cool. Area of a square is side squared, thank you. Okay, I do like you to use that idea of side squared. Remember, beginning of the year, August, let's not go back there, but length times width, I want you to use side squared, very nice. Parallelogram, we've used it a couple times, not a ton, but remember, a parallelogram, it's a rectangle. If we were to take that, it's like a rectangle, I should say. If we were to take that triangle, cut it, slide it over here, what have we just then created? So what's the area of a rectangle then? What's the area of a parallelogram then? It's the same, it's one and the same, okay? You still have to have a perpendicular base and height. Okay, so it's still going to be the same same formula. Okay, they are one and the same. You're not going to use the non-perpendicular side right here. Okay, perpendicular base and height. They are one and the same there. Area of a triangle. And then back to that perpendicular base and height. I don't care which is base and height. I don't care. Just make sure you're using perpendiculars. Last two. These are the two those students always mix up. Good thing we had those blue SAT formula sheets. Your responsibility to remind me to pass out to you guys those on the rest of these assessments this school year. I will. You got to remind me though. I'll forget. They're right here. You just got to remind me.
You could write it on the board.
I don't. No,
You'd
that's
ignore
what.
it.
Here's the reason why. And on the SAT, that's what's going to look like. So I want you comfortable with looking at the SAT. Like, those are carbon copies, okay? So I want you comfortable with looking at those, all right? So it's your responsibility to. So with that, all right, area of a circle, pi r squared, okay? Pi r squared. Got to know the radius, okay? Got to know the radius. Now the last one there is circumference. Julian? 2 pi r. Now, the circumference can be, circumference can be written one other way. I don't know if anybody remembers it. Pi diameter, diameter pi. Because what is the relationship there? 2r is the same thing as diameter. However you want to remember, I don't really care. I just checked how the SAT writes it. The SAT writes it as 2 pi r. But some of you I know have grown up with as pi times the diameter. I don't really care. All right, I've grown up with a 2 pi r. SAT does use 2 pi r. So I'm going to go with that so you're comfortable with that. But it's 2 pi d, it's the same thing. Okay. So we're going to merge our arc work today with some of this circle work. Okay, area and perimeter formulas today into next week. We'll talk about that here in just a few minutes. Okay, flip it. Let's go and let's take number 3 real quick. All right, let's do, no, not 3, let's do 4. Let's do 4. Given the area of a circle, go find me the circumference really quick. Okay? Given the area of a circle, go find me that circumference really quick. All right? If you don't have your calculators today, you will need your calculators. Okay? You will need your calculators. So, area of a circle, go find me the circumference. So again, as I was working on my stuff this morning for the next, again, the rest of April here, it's a ton of circle work. That's all we're doing is circles. Got to know what you got, where you want to go. Where do we want to go? What do we got to have for that? We want to know what? Okay, we got to know the radius, right? Because what are we asked to find? Circumference. You got to know the radius here because we're asked the circumference. Do you know the circumference at all? No. Do we know the radius at all? No, we don't know what the radius is, do we? Now we can find it. It's hiding because what do we do know? You know the area, right? That's about all your area formulas. Okay. Area of the circle is pi r squared. So you got to work it backwards. We've done working things backwards. I know we have throughout the school year. What is it? 25 pi. Back to now your algebra skills. This is a quadratic. We have 4 methods to solve quadratics. Which method are you choosing here? This is obviously a square root one. Okay? So all of the stuff I've done with you, not just to torture Eric this school year, okay, maybe to torture Eric a little bit. All right, but it's been to work up all your skills and maybe to torture Spencer actually quite a bit. Okay, solve by square roots. Got to divide by pi, right? Got to divide by pi. What's going to happen to those pi's? Cancel out. And the square root of 25 is just. No, it's not. Square root of 25 is what? Do I keep the negative on? No. So it is just 5. I know. We do get 2 solutions, but we have context this time, don't we? We toss the negative solution because it doesn't make sense for a negative 5, does it, for a radius? Okay? All right. We got the radius now. So don't we have the circumference? So what's the circumference now? 10 pi. 10 pi. Units are what? Just inches, because circumference is you just walking around the perimeter of the circle, walking around the edge of the circle to where you started at. And that's it. Now, stop right there because it says the directions say in terms of pi. Remember, when we say in terms of pi, I want to see pi in your answers and stop. Go to the next one. What do you want on the next one? You want the area. If you want the area, what do you got to have? Everything really goes back to knowing the radius. As we saw in our formulas a few minutes ago, pi r squared, 2 pi r. You got to know what the radius is. You're always going back to the radius. You don't have it, what you got is circumference. So 2 pi r is what you got. Circumference is 100 pi. Back to your algebra skills. This isn't quadratic, is it? It's a plain old linear equation. There's no r squared up there, it's just plain old linear. What's the radius then? Radius is just 50. Divide by 2 pi, radius is 50. So what's r squared? What is 50 squared then? Yeah, it's a little bit larger one, isn't that? Okay. Go to your calculator if you need to. Never type in pi right here. Okay. It doesn't say anything about rounding. It says all about terms of pi. So if you need to use it, 50 squared is what? Right. 2,500, and then we tack on the pi. Units are inches, but squared, right? Because area is 2 dimensions. Area is everything on the inside of that circle. So this is like if you're trying to paint the inside of the circle this time. That's 2 dimensions. Okay, 2,500 pi square inches. But here, let's go backwards to that arc length. Maybe I didn't necessarily want to walk around that full circle. Maybe I started walking around this circle and I stopped partway. I didn't walk around that full circle, did I? I walked around maybe a fraction of it. Okay, I didn't do the full circumference. I did a fraction of it. That's what we're looking at here today now. Okay, so we didn't do the full circumference. We did what we call is arc length. So what an arc length is a fraction of a circle's circumference. Okay? So today what we're going to be doing here is we're going to do some walking. Okay, we're not going to walk. Alright? But what we're going to do is do a partial walk around the circle. Anytime we do a partial of something, that's a fraction, right? So we're going to talk about doing a fraction of the circumference. That's all I need you to remember for today. That's why on your SAT formula sheet, you're never going to see the arcing formula because it's a fraction of circumference. So, the length of an arc. The length of an arc is just a fraction of our circumference. So, it's the product of the ratio of the blank and the circumference of the circle. So, the ratio of the measure of the arc and the circumference of the circle. So what I mean by the measure of the arc. Come back and we'll create the formula here in just a moment. It's pretty straightforward. It's very straightforward, but we know where we're at in our fraction skills. We love it, right? Okay, maybe not, but it's okay. I get it. Let's do this. I'll come back. We'll create the formula here in a moment. Okay, guys, let's go. Find me the circumference of the circle. You got to know first off what's the big old circumference. What's the circumference of the first circle? Okay. What's the full circumference here? 16 pi is the what? It's the diameter. So therefore my radius is what? 8. Radius is 8. Therefore my circumference is going to be 2 pi r, which is what? 16 pi, right? That's where I was saying a few minutes ago, 2 pi r, pi d, it's one and the same, isn't it? 16 pi inches. So this is where if you had to walk around from point Y, you walked around the full circle, you walked 16 pi inches. I don't know what, that sounds stupid. You walked 50 inches, 50 feet around. okay? Inches, 50 inches sounds stupid too. You walk 50 feet around that circle, okay? That's what that means. But we didn't walk 50 feet. Let's say maybe you walked only from the length of X to Y. Okay? Go calculate me that. So how much did you actually walk then? What does XY represent in terms of that circle? How much? A fourth of it, right? It's clearly a fourth. How do you determine it's a fourth though? It's 90, right? 90 out of how much? Keep that in mind. Okay? A fourth of the full circumference. What's the full circumference? 16 pi. I mean, that's not a crazy fraction, is it? You see clearly it's a fourth. 90 out of 360, fourth of a full. What's a fourth of 16? So Jillian only walked 4 pi of it, a fourth of it. That's not crazy. Okay. How about the other one? What the other one say? You walked how much? X is dy. Where's X? Where's Z? And where's Y? What's that fraction? How do we get 3/4 out of that? That's 90. How much remains? Whoop. 360. We used up 90. How much remains? 270, right? Which is how many degrees? Oh, sorry. Which reduces down to how much? 3/4, right?
No.
3/4. 3/4. 3/4 times the full circle. Full circle was still 16 pi. And what is 3/4 of 16? 3/4 of 16 should be 12. And if you're not 100% sure because it's fractions, what do we have here? We have ourselves a calculator, don't we? 3/4 of 16 still checks out to be 12. And that makes sense because Jillian did 4 pi, Nevaeh did 12 pi. What's 4 plus 12? Makes a full, doesn't it? Okay, let's come back to that. Because what you just did is you found the formula for arc length. What do I mean by that? 1/4 Jillian said was what? 90 out of 360. 3/4 was what? 270 out of. This is always out of how much? The only thing that's changing on us is the arc. So let's go create our formula. You just found your formula. It's a fraction of the circumference. So arc length is the measure of the arc, always out of what? 360. Times what? The circumference. And what's their circumference formula? 2 pi r. Plus it. So that's our formula we're going to run with for arc length. It's a fraction of the circumference. You know what the circumference formula is? 2 pi r. Just take a fraction of it. Okay? We clearly did that a second ago. You said a fourth. You said 3/4. Cool. Let's go do it now down below when it's not as nice of fractions. Okay? That's our formula for today. Box it in, star it, highlight it, go get that henna tattoo. I haven't seen it yet. I haven't seen that sleeve yet. Nobody's going to take me up on that offer. I'm waiting on it.
Nope.
All right, that's fair enough. Let's go do it. Number 7. We're going to walk on this circle on that highlighted part right here. Not the full circle, but let's go calculate the full circle. We're going to first determine what's the circumference of the full circle. What's my radius here? 7. So if we walk the full circle, the circumference is what? 2 times 7, which is 14 pi, right? But we're not walking the full circle, are we? We're walking 225 out of always what? Fraction of a full circle. 225 out of 360. Okay, plug it into your calculator, guys. These are not going to always turn out to be pretty numbers. Never type in pi. So, 225 divided by what? Always 360 times what? 14. Let the calculator do all the heavy lifting. Hit enter, and then change it to what? Fraction. Decimals and pi, decimals and radicals, we never do hand in hand. We do what? Fractions pi, fraction radicals. Math, enter, enter. Somebody get what? 35 over 4. It's going to look ugly. It is what it is, people. 35 fourths pi. Units are yards. Yards, that's it. Okay, in terms of pi. That's a fraction of that circle. 8 points, what was it, 75 I think it was? 8.75 pi, or 35 over 4 pi. Preferably we'd use it a fraction. Okay, next one. What's the full circle? What's the full circumference? 18 pi, right? 2 times 9, 18 pi. But we're not walking the full circle, are we? We're walking 120 over 360, which is a third, I believe, right? I'm not going to reduce it down. But I'm just going to let my calculator do all that work. Don't try to reduce it. If you're going to try to reduce it down, you're going to probably make a good chance you can make a mistake. Let the calculator do all the work for you. I believe it's a third. 120 over 360 times, what is it, 18? I heard a 6, which makes sense because that's a third. And a third of 18 is 6 pi. Alrighty. That's it. That's our new one for today. 6 pi. Okay? Alright, we'll leave it there. Okay, assignment for today.